So Joe J sent us a trig question that is as follows. It says to us here, in triangle M and P, angle M is 90 degrees and the sine of M is 15 divided by 17. Determine, without the use of a calculator, the tan of M, okay? So I think from what you're just looking at, before we even go anywhere, let's first of all construct the triangle. It is a very difficult matrix to work with something that you don't see, right? So advice, always try and create a picture of what these people are talking about. So I definitely see that this is going to be a right-angled triangle, okay? Why? Because angle M is going to be 90 degrees. Now, once I've got that, I can put P anywhere and I can put M anywhere I like, okay? So I'm going to put P here and I'm also going to put M here for no particular reason. Just putting them like that, it doesn't matter. Okay. Now, we were told that the sine of M is 15 divided by 17. Now, angle M is this angle here at the bottom, okay? Now, if you tell me that the sine of angle M is equal to 15 divided by 17, we all know from soccer term that sine is opposite divided by the hypotenuse, okay? This is the opposite side to the angle, and this is going to be the hypotenuse, which means I can now go to my drawing and then label the sides. So the side that is opposite to angle M will have to be 15 units, and the hypotenuse, which is PM, will certainly have to be 17, okay? We don't know what MN is, but using the Theorem of Pythagoras, we can then be able to figure out what the length of MN is going to be. Now, the first question is asking us to work out the tan of M, okay? So if you try to work out the tan of M, you will agree with me that by definition, the tangent of any given angle in a right angle triangle will always be the opposite side divided by the adjacent side. We do have the value of the opposite side, but we don't have the adjacent side. This is why we're going to need to use the Theorem of Pythagoras and figure out what is the length of MN, okay? Because then it's going to be opposite, which is actually 15, divided by the adjacent side, which is MN. Now, how do you work out the length of MN? That's where Pythagoras comes in. Pythagoras said the hypotenuse squared equals to the sum of the other two sides squared. So, which means from what we are looking at, we can then simply claim that your MN squared plus PN squared is MP squared. This is straight from the Theorem of Pythagoras. So, which means MN squared will just be MP squared minus PN squared, okay, which then we can do substitution. The opposite side, which is the hypotenuse, which is PM, is 17 squared, and then PN is just simply 15 squared. And then obviously, if you are looking at MN, you're going to have to also take the square root on both sides in order to figure out what the solution is going to be. So let's call our calculator and ask what is 17, right, to the power of 2 minus 15 to the power of 2, okay? So that's going to give us something pretty awesome, and we're getting 64. Then we have to take the square root of that, which will then leave us with a length of exactly 8, because I'm sure you guys know that the square root of 64 is just going to come out as 8 units, okay? So that means this side that is adjacent to M is just going to simply be 8 units. Let's put it in blue because we just worked it out. Now that means that the tan of angle M will just simply be 15 divided by 8. Simple stuff, right? We move on to 5.1.2. They see the length of NP, right, if MP is equals to 51, all right? If MP is equals to 51. Now, somebody can ask one weird question. The reason why I wanted to do it like this is because I wanted you to see something very exciting about what is going on, right? And this actually goes back to the fact that we were given that the sine of M is 15 over 17. The ratio is 15 over 17. When you divide them, you get 15 divided by 17. So when you get to this point, you're probably wondering, but we know from what we are looking at that NP is 15, okay? How can you ask me for NP if you told me that NP is 15? This is because NP is not actually 15 units. But when you divide that NP with PM, you get 15 over 17. That means if we go back to what we have done so far, right? Because this is very important. We have to give you the concept and then show you what the flaw is in the whole concept. What you're looking at here, this story that says sine of m is 15 over 17, right, tells you that the opposite side divided by the hypotenuse side gives you an answer of 15 divided by 17. I did succeed to answer the question, right? But then you would pick up when you move on that we've got a problem here. How can you ask me something that I'm looking at? Okay? So the reason is because of this. If you work out the sine of angle M, and then you get that the answer is going to be 15 over 17. It is because this was 15 times some variable divided by 17 times some variable. We don't know what the actual length of those sides are. Okay, so which means, like I said, sine is opposite over a hypotenuse. That means Pn, the length Pn, okay, is actually 15k, and the length Pm is 17k. We don't know the actual length of those sides. Okay, we don't know how long they are. We just know when you divide them, you're going to get 15 over 17. Now, calling the other one 15 and calling the other one 17 will be a flaw, right? I hope you guys can see where this whole thing is going. Very important for you to keep that in mind. I wanted you to see what you could do if you knew the actual length of those sides, but we didn't know the actual length. We know the ratio. When you divide them, you'll get 15 over 17, all right? Very important. Now, I'm going to go back on this, and I'm going to say, okay, 15k is the actual length of Pn, and 17k is the actual length of Pm. We don't know what k is. It's a multiple, right, of 15 and a multiple of 17. When you divide them, you get 15 over 17. So what does that mean? That means if you go back to your Pythagoras, you would be looking at 17k here, you'll be looking at 15k here. The final answer will simply be 8k as well. So we don't know what the actual lengths are. That's going to be 8k. Very important for you to keep that in mind. Now, even when you go back and you try to divide 15k over 8k, you would still end up with this 15 over 8 as the value of the tan of angle M. Very important for you to see that. Now, that means when you go back to the actual question 5.1.2, they say the length of NP. We need to find how long is NP if PM is 51. So that means in my triangle now, the actual length of PM is equal to 51 units, okay? Now we are looking for NP. We want to find how long NP is going to be, right? We want to know how much this is, okay? So the ratios need to be the same. Let's go back and try to figure out what that one is going to be out, what that's going to actually amount to. So NP divided by, I'm just going to divide them and try to find a solution from that. I'll do the ratio of PN divided by PM. Right? Pn divided by Pn. Let's reconstruct the triangle so that you guys can see what is going on. There's P here, there's N here, there's M. We said this is 15k, this is 17k. Okay, and now we know the actual length of this, right? The actual length of this is apparently 51. So the sine of angle M is basically 15k divided by 17k. But the sine of angle M can also be written as Pn divided by MP or PM, right? The opposite side divided by the hypotenuse. So I'm going to equate those two ratios because they're both equal to the sine of M, which means 15k over 17k is as good as Pn, which is what we are looking for, divided by MP, which is 51. From here, you just basic algebra. The Pn length is going to be, when you cross multiply that 51, which means the k's are going to cancel, you will just simply have a fraction, okay? In that fraction on top, you're sitting with the length of 15 divided by 17, right? Multiplied by that length of 51. It's giving us exactly 45. So which means Pn is going to have an actual length of 45 units. Very important for you to understand ratios compared to actual values of what is going on there. Very, very important for us to keep that in mind. Okay, cool. So let's move on to the second part of this question. They say simplify to a single trig term. We have to simplify to a single trig term. It's cos x minus 360. Okay, let's just copy that down and then work with it. So we have to do to a single trig ratio. What is the cos of x minus 360 degrees multiplied by the sine of 90 degrees plus x plus cos squared of negative x minus 1. So all this needs to simplify to a single trig ratio. Okay, cool. So these are reduction formulas. Reduction formulas, we've worked with them a long time ago from grade 11. We should understand a couple of things that are going on here. So let's just look at each one of them. So this is actually my advice to you. You'll identify the quadrants for those ones that are okay. When I mean the ones that are okay, anything that says 90 plus 90 minus, 180 plus 180 minus. If you're going to meet one that has got a number, a value that is more than 360, you need to subtract 360. Okay? If you're going to have one that has got a negative special angle there, okay, you're going to have to add 360. Just keep those ideas in mind. And also remember, if it's 90 or 270, the ratio is going to change to its trig ratio. 90 or 270, the ratio changes, but 180 and 360, the ratio does not change. Just keep that in mind. Okay, cool. So now let's go back to this. What do I hate about the first one? It's got a negative 360. To undo the negativeness, I'm just going to add 360 here. Okay? What does that mean? That's going to actually reduce itself. What can you tell me about this? There's 90. That means the ratio is going to change from sine is going to be cosine. Okay? Negative acute angles are found in the fourth quadrant, so I'm not worried about that. I know how I'm going to handle that. All right. So the first reduction, when you add 360 or negative 360, this fixes itself to just the cosine of x. On the second one, 90 plus is the second quad. Because it's sine, sine in the second quadrant is positive. So I get a positive result. So this thing changes because of 90 to its core ratio. The core ratio of sine is cos plus. Anything negative is always positive. If this cos was not a cos, it was any other trig ratio, for the fact that it is square, it will always amount to a positive result. But then in the fourth quadrant, cos is positive. So this is positive twice. It's positive because in the fourth quad, cos is positive. It's also positive because anything squared is always positive. So this is going to be cos squared x minus 1. Okay, the product of these two guys amounts to cos squared x plus another cos squared x minus 1. You add one monkey with another monkey, you're going to get two monkeys. So that's going to be 2 cos squared x minus 1. But what is this? If you've been doing trig enough, you know that this is a double angle of cos. So that's actually cos 2x. No problems indeed on that one. Very exciting question and very simple, straight to the point. All right, so let's move on to the third question. The third question in this list, we're now given the sine, okay, of 2x plus 40 degrees. Sine of 2x plus 40 degrees times the cosine of x plus 30 degrees minus the cosine of 2x plus 40 degrees multiplied by the sine of x plus 30 degrees. All right, so the question says we need to simplify this to a single, write as a single trig term in its simplest form. That's what the question is, all right? We need to write this as a single trig ratio in its simple form. So what am I looking at here? This looks like the expanded version of sine A minus B. Remember, this is actually sine of A, okay, cos of a different angle. That angle 2x plus 40 comes back again here. There it is, 2x plus 40. The angle x plus 30 comes back again. There's x plus 30. That's going to be my angle B. So what am I looking at here? I'm looking at sine A cos B cos A times sine B. That's the expansion for sine one angle subtract another angle. So this is this expansion of sine angle A, which is 2x plus 40, minus angle B, which is x plus 30 degrees. Very awesome stuff. You have to be able to identify these kinds of things, okay? So what do you get from here? Well, this is actually sine. Okay, on the first one, if you see 2x there, of course, when we subtract this, it's going to be 2x minus x, which will just leave us with 1x, right? And then if you go again for 30, you're subtracting 30 there. When you multiply with that minus, it's going to be 40 degrees minus 30 degrees, which leaves you with a value of 10 degrees. So there you have it. I just succeeded to get it to be a single trig ratio with a simplified form. Like, this is just the best I can do in trying to simplify this, right? Okay. So now we're going to move on to the follow-up question. They say now we need to determine the general solution of this, okay? So I want you to see something here. All right, so we are looking at that. We just did the simplification that was required, writing this as a single trig term. Now we need to find a general solution of the following equation. If you look at it, this stuff on the left here, right, is exactly what we began with. It's a follow-up question from what we started with. The stuff you're looking at on the left-hand side is exactly what you started with in that opening statement. Now, we need to take that and equate it to cos 2x minus 20. What have we achieved so far? We succeeded to show that the left-hand side is as good as the sine of x, okay, plus 10 degrees. That's what we succeeded to do. So we're just going to have to take that sine x plus 10 and equate it to the cosine of 2x minus 20 degrees. That's what we have to do here. Okay, so let's go back and check how we can actually find our way around this. So the follow-up question that is asking for the general solution, which is 5.3.2. On the left-hand side, we can see this simplified to sine x plus 10 degrees. On the right-hand side, we are given the cosine of 2x minus 20 degrees. We are required to find the general solution of this thing. Okay, so what I'm going to do here, I'm going to be very sneaky about it. I'm going to use the fact that if you are looking at a trig equation and you happen to find yourself in a position where the sine of an angle is equal to the sine of another angle, right? The only way this statement would be true is if this angle here is equal to that angle here. This is a situation of saying, if the trig ratios are the same, equate your angles. So that's what I'm going to do here. But I can't do it since my ratios are not the same. One ratio is sine on the left, the other one is cos on the right-hand side. Now the question is, if I'm sitting with a cos now, how do I force it to be a sine? Well, you should agree with me that we're going to need to use 90 degrees in this case. So I'll leave the left-hand side as it is, sine x plus 10 degrees. And then I'm going to change the right-hand side to sine. But if you're going to change surname, we need a ring. Here's a ring, because this is actually changing surname, okay? Then there you have it. There's my 2x minus 20 degrees. If you work your way back in reverse and you have to reduce sine 90 degrees minus anything, it reduces the cos of that angle that you're looking at there. So now I'm sitting with a situation where the trig ratios look exactly identical. If they do, I can drop them and equate the angles, which means that now I'm going to say, okay, x plus 10 degrees is equal to 90 degrees minus 2x minus 20 degrees, okay? And because they set general solution, immediately when you equate the angle to add k times 360, and remember to mention that k is the element of integers, right? Immediately when you equate the angles, that is where you start now immediately introducing the whole story of the k times 360 to make it a general solution. Okay, cool. Now from here, it's just a simple play of numbers to try and make x a subject to the formula. I think you'll agree with me, you're going to have x plus 10 degrees is 90 degrees minus 2x plus 20 degrees. This adding 2x on both sides, you're going to have 3x on the left, and then subtracting 10 degrees on both sides, I'm going to be sitting with 90 plus 20, that gives us exactly 110. If you subtract 10, it goes back to exactly 100 degrees. Plus, don't forget what we said, this is a general solution problem, so we need that k times 360 degrees to be part of what is going on here. So divide everyone by 3, then finally your x comes out as 100 over 3, okay, degrees, plus k times 120 degrees. So very important because k is the element of integers. Now someone is asking, is this the only way of doing it? Well, no. If you want to change cos to look like sine, you don't have to use only 90 degrees minus, okay? You can also use 90 degrees plus, because 90 degrees plus leads you into the second quadrant, and sine is positive there, so it will still reduce back to positive cos. What do I mean? Let's go back to it. So I'm basically saying to you, we can again take this line, exactly this line, and rework it differently. Instead of using 90 degrees minus, we can again use 90 degrees plus. That's 2x minus 20 degrees. That will still also reduce to positive cos if you do your reductions very well. I think you guys need to be very good at reduction formulas. If you are able to do all that, this is going to be very fun and exciting. Okay, so let's go and do that part. This is actually an alternative to the solution. We find in the general solution. So, which means what? We just simplified that sine of x plus 10 degrees can be simplified to sine of 90 degrees plus this time of the same angle that they gave to us, which is 2x minus 20 degrees. Remember, this comes from cos of 2x minus 20 degrees. So I'm just simply saying that cos 2x minus 20 comes from 90 plus 2x minus 20. 90 changes the name of the ratio. 90 plus is in the second quad, so this is actually changing back to what we want. The ratios look the same. If they look the same, you are allowed to start equating the angles at this point. So there is 90 degrees plus, okay, 2x minus 20 degrees. Immediately, once you get here, because they said general, add that 360 part. Remember, k is the element of integers, okay? Then you just simplify and then you're going to get your answer finally. I think from this, when I subtract 2x on both sides of the equation, I'll get minus x on the left-hand side. And then that's 10 degrees. If you do 90 minus 20, it's going to be 70. You minus 10 again. It amounts straight to 60 degrees because this is going to be negative on the right-hand side. 90 minus 10 is 80 minus 20 gives you 60 degrees. Plus k times 360 degrees. We don't like negative x, so x is going to be negative 60 minus k times 360 degrees, where k is the element of integers.